heating curve of a liquid. This section is not actually anything new, but it combines several topics from both this chapter and our thermodynamics chapter. We have previously learned how to use the specific heat to calculate the change in heat within a phase. We just learned how to calculate the heat change for a transition in phase. Now let's combine these concepts to determine the heat change as we go in between phases. So for instance, going from a liquid at a temperature that is well above its freezing point, down to a solid below that to a temperature that is below its freezing point. To do this, we must look at each step individually. We can create something called a heating curve, which just illustrates that each step of the process is handled with its own set of constants. Whenever we are in a particular phase, such as from point A to point B, we use the specific heat equations we discussed in thermodynamics. Whenever we are changing phases, such as from B to C, where it is melting but not changing temperature, we use our heats of melting or vaporization, just depending on what phase change we're in. If you go through several phases, such as going from point A to point D, you must use the temperatures and the heat capacities for each phase separately. Let's do an example of this, and I think it'll make more sense. Take a moment and read through the problem. I would give you all of the constants in this table. To do this problem, you must do each step separately. Finding the heat it takes to heat a solid to the liquid and then to the gas, as well as finding the heat it takes to melt and boil. Once you get each of these completely on its own or separately, then you can find your Q total. So we'll find our Q of the solid, which heats it as a solid. We'll find our Q that it takes to melt the solid. We'll find our Q that it takes to bring our liquid up to its boiling point. Then we'll find the Q that it takes to vaporize it. Then we'll find the Q that it takes to heat the gas. We'll do these using all of the equations that we already know. For each within its own phase, we'll use Q is equal to mc delta T. You'll just have to be very careful to use the right C in the right temperatures. As we're changing phase, we'll use the formulas that we just learned about, our heat of fusion and heat of vaporization. Pause the video now and see if you can try this on your own before watching me do it. You are combining things that you already know, and so you may be able to make it through without my help. You might make a mistake or two, but that's going to help you learn for the future. Okay, let's start with the solid and work our way up. We know that heating a solid uses the specific heat capacity equation, Q equals mc delta T. And so we're going to use this while carefully filling in the moles, the specific heat capacity of the solid. So you must make sure you grab the solid and the change in temperature. Make sure that when you use the change in temperature, you're not using the entire range. You're only going from the starting point of 155 up until the point where it melts at 176. This gives us our value for just this section. We can now take the heat required to melt the sample. We'll multiply our heat of fusion by our number of moles to get our value. This gets us to the liquid. We must heat the liquid from its melting point to its boiling point. So we will do that and fill in the C for the liquid from the table. For the temperatures, you need to make sure to only include the temperatures from the point where it melted to the point where it boiled. So we go from 176 to 338. To save some room on the slide, I'm going to go ahead and put these in the equation above. Now let's keep moving on. We need to find our Q of vaporization. For this, we use our H of vaporization and our moles to find out how much heat is required to boil the sample. Be careful that you're grabbing the heat of vaporization and not fusion. Lastly, we find out the heat that is required to heat our now gas sample from its boiling point to the final temperature of 375. We'll very carefully pull the C of the gas from our table, fill in the moles, and then use our temperature change from the 338, where it was when it started boiling, to the 375. Now that we have all of these values, we have to add them up. We get our final value and round to our proper number of sig figs. You'll notice I trace sig figs with a little underline. And we end up with 34,000 joules. You can, of course, change this into kilojoules if you want. You also could have done all of the calculations in kilojoules. Just be sure that you do all of your calculations in one unit or the other and that you aren't combining them. In review, whenever we are heating species through a phase change, we must use different specific heats for each portion of the process, and then use either the heat of vaporization or fusion, or both sometimes, as in the very long example that we just did, when the phase change actually occurs.